Hello everyone, welcome back to Science with Kanush. Today we are diving into a super important chemistry topic, stoichiometry. So, whether you are preparing for exams or just love chemistry, this video will make everything crystal clear. So, let's get started. First of all, what is stoichiometry? So, stoichiometry is the branch of chemistry that helps us to calculate how much of each substance is involved in a chemical reaction. So, for example, how much of the reactant will be required to carry out the reaction, and after the reaction has been completed, what amount of product will we get. And it's all about balancing equations, finding quantities, and understanding proportions. So let's start. So, first of all, when we write the formula of the elements and compounds, for elements we use the chemical symbols which are given in the periodic table. And for compounds, what we do is that combine the elements which are used to form that molecule, and we use using their valency. So I'll give you guys an example. For example, we have H2O. So we use crisscross method over here. We have H and O. The valency of hydrogen is 1 and the valency of oxygen is 2. So by crisscross, I mean like this. It goes like this and this goes here. So it becomes H2O. I'll give you guys another example. So we have carbon and we have oxygen. The valency of carbon is 4 and the valency of oxygen is 2. Again, we go through the crisscross method. So we have C2O4, C2O4. But this then gets simplified to CO2 because 2 is to 4. When we simplify this ratio, we'll get 1 is to 2. So we get CO2. Then we have two types of formulae. We have molecular formula and we have empirical formula. Molecular formula shows the exact number of each atom and in a molecule. So, for example, the molecular formula of glucose is C6H12O6. And we have empirical formula, which I'll be explaining when I start with the supplement concepts because it's not for the core students. And here we have the example of NaCl. So, molecular formula shows us the ratio, the exact ratio of the atoms present in a molecule. So, in a molecule of NaCl, as we can see here, there are 1, 2, 3, 4, 5, 6, 7, 8 molecules of Cl. 8 atoms of Cl and 8 atoms of sodium. So it's exactly the same. That's why the ratio is 1 is to 1, and hence the formula is NaCl. Okay, now we have word equations. So we construct word equations in which we have the reactants and products. We write the full names of the full chemical names of the reactants and products when we are writing a word equation. So the reactants are the substances on the left hand side and the products are on the right hand side. So here we have an example, sodium hydroxide plus hydrochloric acid. So the plus sign, we use it to add more and more reactants or more products. That's like quite of a common sense thing. So the reactants over here are sodium hydroxide and hydrochloric acid, which is then giving us sodium chloride and it's giving us water. So sodium chloride and water are the products. So when we represent the arrow, I have heard quite students saying that sodium hydroxide plus hydrochloric acid equals to sodium chloride and water. So that's not the case in chemistry. We use when we have the arrow, we say it gives us or it forms or it produces. So we don't say equals to in this condition. Then moving over, we have symbol equations. So symbol equation uses the formulae of the reactants and products. Instead of writing the entire sodium hydroxide, I'll be just writing NaOH. That is the symbol, the formulae. Okay. And for its hydrochloric acid, we'll be using plus HCl and then sodium chloride, NaCl plus H2O. So this is how we turn this word equation into a symbol equation. Now, when we write a simple equation, we should ensure that the reactants are on the left side and the products are on the right side, as it is in word equation as well. Then we write some nonmetals as H2, O2, N2, F2, Cl2, Br2, I2, because these are diatomic molecules. So if a substance is reacting with hydrogen, we'll not just write H, but we have to write H2. So for example, here we have that sulfur is reacting with oxygen. So instead of writing only O, we have to write O2. So when an element like these non-metal molecules, uh, when we are just writing them as in their elemental form, they are not with any other element combined, we always write it as a diatomic molecule. So then we have to include state symbols as well. We have the state symbols as solid, which is represented by S, is solid. Then we have gas, which is G. We have L for liquid. And we have AQ for aqueous. Now, many of you will be confused that what is the difference between liquid and aqueous. So, in liquid, in aqueous, any substance is dissolved in water. So, that time we say that it is aqueous. But if the compound is in a liquid state, it is not dissolved in water, we'll use the L to represent that. Okay, generally we have that metal compounds will always be solids. There are a few exceptions to that, and ionic compounds will usually be solid. Non-metal compounds can be solid, liquid, or gas, so it depends on the information given in the question. Now, we have questions in which they state us that the precipitate is formed. When they use the term precipitate, we should understand that they are talking about a solid. So, PPT. I'll just write the short form of precipitate as PPT. So when they say precipitate, that means a solid is formed. Okay, and we have to balance our symbol equation. So balancing symbol equation, we have this equation. This is a self-balance equation because we have one atom of Na over here, we have one Na over here, we have one one O here, and we have one over here. We have 2H over here, so we have H2, that is 2H over here as well. We have a Cl over here, and similarly we have a Cl over here as well. Okay, now but when we talk about this equation, Fe2O3 plus 3C gives us 4Fe plus 3CO2. So for this one, Fe2 we have 2Fe and we had 1Fe over here. So we had to equalize it. So maybe we could try trial and error method. Let's say we wrote 2 over here. Then we have 3 oxygen over here and we have just 2 oxygen here. So how can we balance that? We can turn both of them to 6. So I wrote a 2 here and I wrote, so we got 6 oxygen here. Look, 2 times 3, so we got 6 oxygen. And here also we got 6 oxygen by writing 3. Okay, so 3 times 2 is also 6. But then our trial and error method got wrong here because now the number of Fe is 2 times 2, which is 4. So we have to write a 4 over here as a coefficient. Then we have the number of carbons. So we have 3 carbons here. So we'll just put a 3 over here. So this is how we balance the equations. Balancing equation actually requires a lot of practice and a lot of time to understand because it's basically trial and error most of the time. So let's move to the next thing, which is the empirical formula. So as I told you that the molecular formula shows the exact number of atoms in a molecule, but in an empirical formula, it is the simplest whole number ratio of atoms. So for molecular formula, we gave the example as C6H12O6 for glucose. But the empirical formula of glucose is going to be CH2O because that's the simplest ratio. We have C6H12 O6. So these all can be divided by 6, right? 6 divided by 6 is 1. So C. 12 divided by 6 is 2. so CH2, and 6 divided by 6 again is going to be O. So this is the empirical formula. Empirical formula. Okay. Then we have the formulae for ionic compounds. So for ionic compounds, we use the ion charges to deduce the formula. Okay. Um, so for example, we have NaCl. The ion charge of Na is +1, and for Cl it's -1. And again, we have the crisscross rule. So the -1 goes to Na and the +1 goes to Cl. But we don't include minus and plus when we are writing the formula, so we write it as NaCl because it's 1 and 1. We don't need to write 1 specifically. When we write NaCl, it's considered as 1. And now we have Mg as +2, and for Cl we have -1. Again, we do the crisscross method. So Mg gets 1 and Cl is 2. So MgCl2. Now we have symbol equations. We use state symbols. Okay. So in aqueous solutions, ionic compounds actually dissociate into their ions. This means that they separate into their component ions. For example, hydrochloric acid and potassium hydroxide. So hydrochloric acid forms H plus ions and Cl minus ions. Now I have said aqueous over here and aqueous over here and aqueous over here because as I told you that it dissociates when it is in an aqueous solution. That means when it is put into water. So we don't write liquid, we write aqueous when we are writing the dissociation over here of HCl and KOH. So KOH gives us K plus ion and OH minus ion. Now it is important that we can recognize common ionic compounds and their constituent ions. So acids such as HCl and H2SO4, so it will give us H plus and SO4 2 minus. Those are the ions produced from H2SO4. Group 1 and group 3 hydroxides, example sodium hydroxide. So it gives us Na plus and OH minus. And soluble salts, example potassium sulfate or sodium chloride. So NaCl, it will give us Na plus and Cl minus ions. Okay. Now, when we are writing an ionic equation, we have to write the full balance symbol equation, and we replace the ionic compounds in the balance symbol equation with the component ions. And then we remove any ions that appear on the both sides of the equation. So we have an example here. We wrote a balanced chemical equation. This is the displacement reaction, okay, of aqueous chlorine and aqueous potassium iodide. So in the question itself, it's written that write the ionic equation for the displacement reaction of aqueous chlorine and aqueous potassium iodide. So it's very simple. We can write the state symbols as well, aqueous and aqueous, again aqueous, and here also aqueous. Now, as told in the steps, that we replace the ionic compounds in the balance symbol equation with the component ions. So when we write Ki, we have to write 2K plus, and this 2 also will go with the iodine. So 2I minus iodide ions. And Cl2 is not an ionic compound, so it's just a molecule. We'll write it as it is, Cl2. Again, we have KCl, that's an ionic compound, so 2K plus and 2Cl minus. And I2 is a molecule, that's why it goes as it is. Then we have to cancel out 2K plus and 2K plus because it's repeated on both the sides. We'll be left with 2I minus, Cl2 aqueous, 2Cl minus aqueous, and I2 aqueous. So this is our balanced ionic equation for this reaction. So ionic equations should always have state symbols. That's a rule of ionic equations. Now let's move on to the next thing, that is the relative masses. So relative atomic mass. This is the average mass of an atom compared to 1/12 of a carbon-12 atom. For example, chlorine has an AR of 35.5. Then we have the relative molecular mass. Add up the values of the AR of all the atoms in a molecule. For example, we have water. Okay, so the mass of hydrogen is 1 and we have 2 atoms of hydrogen. So 2 times 1 is 2 plus 16 will get 18. And for CO2, we have carbon AR as 12 and the AR of oxygen is 16. But as we have 2 atoms of oxygen, we'll write 16 times 2, that is equal to 44. Okay, then we have the reacting masses and proportions. So we have 4 grams of hydrogen because 2 times 2, 4. Then we have 32 grams of oxygen, 16 times 2 is 32, which gives us 36 gram of water. So this is how we get the reacting masses. That's basically using the ratio method. Now let's discuss moles. A mole is a measure of the amount of a substance. 1 mole contains 6.02 into 10 raised to 23 particles. This is called the Avogadro's constant. Avogadro's constant. Avogadro's constant. Okay, and we have a formula which is number of moles is equal to mass divided by molar mass. So for example, we have 36 gram of water and we have the molar mass of water is 18. So 36 divided by 18 is equal to 2 mole. The number of moles is equal to the volume divided by 24. The volume should be measured at room temperature and pressure. So this is very useful when we are calculating gas volumes in reactions. And then we have number of particles is equal to number of moles into 6.02 into 10 raised to 23. As I have told earlier that 1 mole contains 6.02 into 10 raised to 23. So 2 moles will contain 12.04 into 10 raised to 23 particles. Right? And then we have number of moles is equal to concentration into volume. This is when we are talking about liquids. So when we talk about liquids, we use this formula. Then we have the percentage yield and purity. These are the key factors when we are performing experiments. So percentage yield tells us how efficient a reaction is. Percentage yield is equal to actual yield divided by theoretical yield, and we multiply it with 100 to get the percentage. Whenever we calculate percentage, we have to multiply it by 100. Then we have percentage purity. So percentage purity is the mass of pure substance divided by the total mass, and we multiply it with 100 to get the percentage purity. So these are the key formulas of this chapter and these need to be memorized. So we are done with the stoichiometry concepts, but I would like to practice some questions. So these are the past paper questions and I have wrote the paper code as well. So let's do this. Let's try doing this. On the product side, we have 4 hydrogen and here we have 2 hydrogen. So we just multiply by 2. We'll get 4 hydrogen here as well. Then on the product side, we have 2 oxygen over here and we have 4 oxygen over here. So that becomes 6 and then we'll write 3O2 because 3 times 2 is 6. Okay, so we have balanced this equation. Now let's move over to the next question. Okay, now the next question, we will have 4.8 gram of magnesium. Okay, gram of Mg is giving us 8 gram of MgO when it is reacting with excess oxygen. Now we need to get the minimum mass of magnesium which is needed to produce 24 gram of magnesium oxide. So now we are producing 24 gram of magnesium oxide and we know x gram of magnesium. So here, if you know, we can use the we would take this thing over here in multiplication. So 4.8 times 24 is equal to 8 times x. Okay, and for x we'll be doing 4.8 times 24 divided by 8, which is gonna give us, I'll just get my calculator. Okay, 4.8 times 24 divided by 8. We'll be getting 14.4. So the answer to this question is 14.4 grams. Now we'll move over to the next question. This is again, we have to write the state symbols in this one. So magnesium carbonate, large pieces, that means this will be solid. To dilute hydrochloric acid, that means HCl is going to be aqueous. Dilute means that it is added with water. Measures the volume of carbon dioxide gas, that means carbon dioxide is gas. And H2O is always going to be liquid. Okay, so we are done with this. Let's move on to the next. Now this is an extended question. Okay, so calculate the number of moles of HCl in 25 cm cube of 0.4 mole per dm cube of acid. So for this, first we have to convert cm cube to dm cube, and for that we have to divide it by 1000. So when we divide it by 1000, we'll get 0.025 dm cube. And then, like I told you, N is equal to concentration, which is C, into volume, which is V. So concentration is 0.4 times 0.025. We'll get the answer as 0.01 mole. 0.01 mole. Now they are saying determine the number of moles of carbon dioxide gas given off. We have the number of moles of HCl. HCl we know. And we have to get to know carbon dioxide. This is in the ratio of 2:1. So this is 0.01. And when we divide it by 2, we'll get it for 1. Okay, so this will be 0.005. 0.01 divided by 2 is equal to 0.005. Then the volume of carbon dioxide gas given off in cm cube. So we have N is equal to V by 24. We have to get V, which is equal to N 0.005 times 24. But again, we times it with 1000 to convert from dm cube to cm cube, and we'll get 120 as the answer. So we are done with this question as well. Let's move over to the next question now. So this is our next question. We have that ethanoic acid is a carboxylic acid and it reacts like a typical acid. So when a typical acid reacts with a carbonate, we get a salt, which is our sodium ethanoate, and we get carbon dioxide gas, and we'll get water. Carbon dioxide and water. Let's move over to the next question. So we have to complete the chemical equation for this reaction when aqueous chlorine reacts with aqueous potassium iodide. Okay, so we have I2 over here. So we'll put 2, so our iodine is balanced. Now we have 2 potassium over here and 1 potassium here. So we'll put 2 here as well. We have 2 potassium on the right hand side, 2 potassium on the left hand side. We have 2 Cl on the right hand side, we have 2 Cl on the left hand side. We have 2 iodine on the right hand side and 2 iodine on the left hand side. Hence the equation is now balanced. So let's move to the next question now. Again, we have the word equation for the reaction of hydrochloric acid with calcium oxide. So when hydrochloric acid will react with calcium oxide, it will give us calcium chloride, which is a salt, calcium chloride, and it will give us water. And now the next question. So in this question, we have to calculate the relative molecular mass of ZnC4H10. We have to write the number of atoms. It's given for zinc, we'll do for carbon. So the number of atoms of carbon is 4 and the relative atomic mass of carbon is 12. So 12 times 4 is equal to 48. And then we have 10 atoms of hydrogen and the relative atomic mass of hydrogen is 1, so we'll have 10. Now when we add all of these, we'll get the relative molecular mass. So let me do the addition. 65 plus 48 plus 10, it gives us 123. So that's the relative molecular mass of ZnC4H10. Now, in this question, we have that 0.2 gram of copper carbonate is used to give 38 cm cube of carbon dioxide. We have to calculate the volume of carbon dioxide produced when 0.5 gram of copper carbonate is used. So let's make an equation. 0.2 gram of CuCO3 is giving us 38 cm cube of CO2 carbon dioxide. Then 0.5 gram will give us X of carbon dioxide. Now we'll do 0.2 times X is equal to 38 times 0.5. So when we solve this, 38 times 0.5 is 19 divided by 0.2 is equal to 95. 19 divided by 0.2 is equal to 95. So we'll get 95 cm cube of carbon dioxide gas when we use 0.5 gram of copper carbonate. So now we have the Void equation for the reaction of nitric acid with calcium hydroxide. So when calcium hydroxide reacts with nitric acid, we get calcium nitrate, and nitric acid is basically HNO3 and CaOH. So we'll get calcium nitrate and water. Let's move over to the next question. Sodium reacts with oxygen to form sodium oxide. Complete the chemical equation for this reaction. So we have 2 oxygen over here. We can balance it by putting the coefficient 2. And then we'll have 4 sodium atoms. 2 times 2. So 4. And we put 4 over here. Again, this equation is now balanced. So let's move on to the next. Okay, we have the similar type of calculating the relative molecular mass. We have 2 atoms of sulfur. 2 times 32 is equal to 64. And we have 3 atoms of oxygen. So 16 times 3 is equal to 48. And when we add all of these, we'll get 68 plus 48 plus 64 plus 46. We get 158 as our answer of the relative molecular mass of Na2S2O3. And now the next question is, when 0.11 gram of calcium carbonate is used, 25 cm cube of carbon dioxide is produced. So how much is the mass of calcium carbonate needed to produce 100 cm cube of carbon dioxide gas? 0.11 gram produces 25 cm cube. X gram will produce 100 cm cube. We'll do cross multiplication. So we'll get 0.11 times 100 is equal to 25 times X. So we get X as equal to 0.11 times 100 divided by 25. which is going to be equal to 0.44. So 0.44 gram of calcium carbonate is needed to produce 100 cm cube of carbon dioxide gas. Now let's move on to the next question. So again, we have the next question as that complete the chemical equation for the reaction of sodium with chlorine. So 2Na plus Cl2 gives 2NaCl. This is a balanced chemical equation for this reaction. Now we'll move to the next. We again have a word equation and it's the same one if I'm not wrong. Hydrochloric acid plus calcium carbonate gives us calcium chloride, plus carbon dioxide plus water. And now we'll move to the next question. So 0.5 gram of calcium carbonate decomposes to give 120 cm cube of carbon dioxide gas. Calculate the volume of carbon dioxide gas produced when 0.1 gram of calcium carbonate is used. So 0.5 gram is giving us 120 cm cube. So 0.10 gram will give us x cm cube. Again, we'll do cross multiplication. So 120 times 0.1 divided by 0.5. That's going to be 24. So 24 cm cube of carbon dioxide is produced. Okay, and now we'll move to the next. Complete the chemical equation for the reaction when lithium reacts with nitrogen to produce lithium nitride. So we have N2 over here. So we put 2 over here. 2 times 3 is 6. So 6 atoms of lithium and hence we put 6 here. And now we'll move to the next question. We again have the calculation of relative molecular mass. So for hydrogen we have 5 atoms, for oxygen we have 2 atoms, for lithium we have 2 atoms. 5 times 1 is equal to 5. 16 times 2 is equal to 32. 7 times 2 is equal to 14. So now let's add all of these. We'll get 87 as the relative molecular mass. And now the next question. So this is the extended question. We have to calculate the number of moles in 25 cm cube of 0.2 mole per dm cube NaOH. We use the formula N is equal to Cv. Before that we convert this volume into dm cube. So 25 cm cube is equal to 0.025 dm cube. We basically need to divide by 1000 to convert from cm cube to dm cube. So concentration is 0.2 times 0.025. That's going to be equal to 0.005. 0.005 moles of NaOH. Determine the number of moles of H2SO4 that react with NaOH. So the molar ratio here is 1:2. We can see that from the equation. Here it's 1 and here it's 2. So the molar ratio is 1:2. NaOH is 0.005. So the moles of H2SO4 will be half of that. That will be 0.0025. So we'll have 0.0025 moles of H2SO4. Now we have to calculate the concentration of H2SO4. We have the volume of H2SO4 as 20 cm cube, right? So we have to calculate the concentration. Sorry, not the volume, the concentration. We have the volume as 20 cm cube. N is equal to Cv. We know that 20 cm cube is gonna be equal to 0.020 dm cube. C is gonna be n by v, n is 0.0025 divided by 0.02, which is equal to 0.125 mole per dm cube. So the concentration of H2SO4 is 0.125. Now we'll move to the next question. So here we have to balance the chemical equation. So let's try balancing this equation. We have SO2 over here. There is 2 atoms of oxygen, so we can put it 2 over here. 4 atoms of hydrogen on the right hand side, so 4 on the left as well. We'll write the coefficient 2 because 2 times 2 is 4. And sulfur in total will be 2 over here, 1 over here, so 3 sulfur. Okay, now let's move on to the next. Now we have the empirical formula calculation. This is a very important question, so let's get on to it. So for this question, first what we will be doing is 48.65 divided by the AR, the atomic mass of carbon, which is 12, and hydrogen we have 8.11 divided by 1, and then we have oxygen 43.24 divided by 16. So when we calculate this, we'll be getting 4.05, 8.11, and 2.7. So 2.7 is the smallest of all, so we'll divide all of these with 2.7, and we will be getting 1.5, 3, and 1. Now in a formula we cannot write decimals, so we can multiply this by 2. So we'll be getting 3 is to 6 is to 2. So our empirical formula will be C3H6O2. C3H6O2. Now the next question. The next question says that ester Z has the empirical formula C2H4O and a relative molecular mass of 88. So first we have to calculate the empirical formula mass, which will be 12 times 2, which is 24, plus 4 plus 16, which is equal to 44. Now we have to divide the relative molecular mass with the empirical formula mass. So 88 divided by 44, which gives us 2. Now we have to multiply the empirical formula with 2. So that means C4, and then 4 times 2 is 8, so C4H8O2. So this is our molecular formula. Now let's move to the next. We have to calculate the number of moles of in 20 cm cube of 0.05 mole per dm cube HCl. So we'll convert this cm cube to dm cube first, which is equal to 0.02 dm cube. N is going to be equal to 0.05 times 0.02. That is 0.05 times 0.02, 0.001. Now determine the number of moles of CaOH twice in 25 cm cube of the lime water. So we can use the so here we will be using the molar ratio, which is 1:2. This is 0.001, and this will be 0.001 divided by 2. That is 0.0005. That's the number of moles. Now calculate the concentration of COH twice in mole per dm cube. So when we calculate it in mole per dm cube, we will again be using the formula N is equal to CV. The volume is 25 cm cube, which will be equal to 0.025 dm cube. And then we'll get concentration as 0.0005 divided by 0.025, which is equal to 0.005 divided by 0.025 is 0.02 mole per dm cube. Now we have to determine the concentration of COH twice in gram per dm cube. So for that, we will be multiplying this value with the MR of COH twice. So first we have to calculate the MR of COH twice. That will be that will be 74. So 74 times 0.02 is equal to 1.48. So the concentration in gram per dm cube is going to be 1.48 gram per dm cube. Let's move on to the next question. So fluorine reacts with sulfur to form a compound which has 25.2% sulfur by mass and a relative molecular mass of 254, and we have to determine the molecular formula of this compound. So for that, first we have to get the percentage composition of fluorine, and to do that we'll be doing 100 minus 25.2, which is equal to 74.8%. And then we have to convert the mass into moles, like the percentage into moles or the mass into moles. So that will be 25.2 divided by 32.1, which is the molar mass of sulfur, or if we can just take it 32. And then we have the mass of fluorine, which is 74.8 divided by 19. So here we will have 0.785 and 3.937. So we'll divide it by 0.785, which is the smallest value, and we'll be getting 1. And this will be getting 3.937 divided by 0.785, we'll be getting approximately 5. So our empirical formula will be, I'll just write it as EF, which will be SF5. Now we have to calculate the empirical formula mass. So our empirical formula mass is going to be 127.1. Okay, so when we divide 254, the molecular mass divided by the empirical formula mass, we'll be getting approximately 2. Then we multiply the empirical formula by 2, so we'll get S2F10, because 5 times 2 is 10. So S2F10. Now we have the next question. Now this question is of balancing the chemical equation. So calcium is already balanced. We have 2 chlorine here, so we'll put a 2 over here. We have 2 nitrogen on this side, and hence 2 nitrogen here. So 2 times 3 is 6 over here, and 4 times 2 is 8 over here. 8 plus 2, 10. So here we have only 6, so we have to have 4 more hydrogen. hence we'll put 2. So our oxygen is also balanced and all the other atoms are balanced as well. So let's move on to the next now. Now again we have the calculation of the empirical formula. So 58.82 divided by 12, 9.8 divided by 1, 31.37 divided by 16. So 58.82 divided by 12, that is 4.9. This is going to be 9.8, and 31.37 divided by 16 is 1.96. So we divide each value by the smallest, 1.96, divide by 1.96 and divide by 1.96. So when we divide 4.9 by 1.96, we'll get 2.5. When we divide 9.8 by 1.96, we'll be getting 5. And when we divide 1.96 by 1.96, we'll be getting 1. But again, now we have 2.5 with decimals. We can't do that, so we have to multiply this by 2. So we'll get 5 is to 10 is to 2. That will be C5H10O2. That's our empirical formula. Now we'll move to the next question. So ester Z has the empirical formula C3H6O and a relative molecular mass of 116. So 12 times 3 plus 6 plus 16 is equal to 58. So 58, 116 divided by 58 is equal to 2. So we'll multiply the empirical formula with 2. That will be C6H12O6. C6H12O2. So that's our molecular formula. Now we have the next question. So we have the titration calculation over here. So in this we are making the crystals. Hydrated copper sulfate is made by reacting copper oxide with dilute sulfuric acid. The overall equation is shown. 50 cm cube of 0.2 mole per dm cube dilute sulfuric acid is heated in a beaker. Powdered copper oxide is added until the copper oxide is in excess. Aqueous copper sulfate is formed. The excess copper oxide is separated from the aqueous copper sulfate. The aqueous copper sulfate is heated until a saturated solution is formed. The saturated solution is allowed to cool and crystallize. The crystals are removed and dried. Calculate the maximum mass of copper sulfate crystals CuSO4 5H2O that can form using the following steps. So first we have to calculate the number of moles of H2SO4 in 50 cm cube of 0.2 mole per dm cube H2SO4. So 50 cm cube is equal to 0.05 dm cube. Number of moles is equal to 0.05 times 0.2, which is equal to 0.01. So 0.01 number of moles of H2SO4 are present. Now deduce the number of moles of CuSO4 times 5H2O that can be formed. So according to the molar ratio, it's 1:1. So it will be the same, 0.01 moles. Now the MR of CuSO4.5H2O is 250. Calculate the maximum mass of CuSO4 5H2O that can form. So for doing this, we have the uh, N is equal to M by MR. So mass is going to be equal to 0.01 into 250, which is equal to 2.5. So 2.5 grams of CuSO4 5H2O that can form. So this is the end of the video. We have completed the stoichiometry chapter of IGCSE chemistry, and it's a very important chapter. I hope this breakdown helps you tackle chemistry with confidence. Don't forget to like, share, and subscribe to Science with Kanush for more amazing content. If you have any questions related to moles or anything we have covered today, do drop them in the comment section, and I'll see you in the next video.